Well, hello everybody, and happy Sunday to you all. We are under the big thaw, so that's good, coming out of a very challenging week. So what I've decided to do here, as you look at the updated schedule, is I'm going to give you a brief overview of natural gas and nuclear power, and we'll upload this as an asynchronous lecture. This will not be on the exam next week. I think it's just fair to keep things uniform in terms of what is a synchronous lecture and what is not. So this is still important in that it provides context and background. And let me start off with this combined coverage of natural gas and nuclear, just with a couple of thoughts about what has happened in the past week, because obviously it's sort of really interesting timing when we're covering energy in this class, and we go through what we've just experienced in terms of major power outages over such a cold period. Again, this is obviously an environmental course, and I don't want to get too far down a rabbit hole in terms of power generation and electrical engineering, because I'm not one of those. But I think it's useful to just give a quick overview of what happened in the last week, and then we'll talk about natural gas and nuclear. Let me just start here by giving you a couple of sets of data or some information on how much generation capacity we have in Texas, and then how much generation actually occurred in 2020. So just to update you on the latest statistics from the Energy Information Agency, 57.4% of all of our installed capacity, in other words, all of the power plants in Texas, 57.4% of those are natural gas. The red number in brackets here represents how much of our electricity in Texas in 2020 came from that particular source, right? So we've got, something like 77,000 megawatts of natural gas power plants in Texas. In 2020, 51% of our electricity came from natural gas. Wind is now the second largest source of installed generation capacity. Almost 21% of the total amount of energy that can be generated in Texas is wind. In 2020, 24.8% of the total generation of our portfolio came from wind. So don't be confused by that. I know you may look at that and go, well, hang on, how can 25% be generated when we only have 21% installed? Remember, we're just looking at the relative contribution from these sources over a particular given period. You can see how dramatically different coal has become in terms of its importance in Texas. When you go back 20 years, coal was something like 45% of our generation capacity. We now have almost just under 15% of coal is installed. 2020, we got 13.4% of our electricity from coal. Nuclear, 3.8% is installed, almost 5%. Solar, even though this is rapidly growing, it's still a fairly small fraction. 2020, almost 4% of our electricity came from solar. And then there's a combination of hydro, biomass fire units. And in 2020, these accounted for just under 2% of our electricity. So in terms of what has happened in the last week, right, we've got to look at the big players here of natural gas, wind, coal, nuclear, and solar. Those are the big ones in terms of where we get our electricity from. So I've downloaded some data here, and let me just turn on the annotation tool, because this is a fairly complicated chart, but I hope really instructive. On the top here, this curve, this shows the generation of electricity, okay, and this is expressed in terms of megawatt hours. So if you have a power plant that can generate 1 megawatt of electricity and it runs for an hour, of course, it's generating 1 megawatt hours of energy. So on the top here, what you see in yellow and blue, that the dark blue is the demand, the yellow line is the actual amount of electricity that is generated. And the light blue, the little stippled area here in light blue, is what the predictions were, the 24-hour predictions of electricity. So you can hear, you see we're going back to, there's a break here first. So we're going back to the 1st of February here. And you can see that the demand in solid blue and the amount that's actually supplied in yellow are lying on top of one another. That's great, right? That means the demand is being satisfied by the amount of electricity that is actually being generated. And we start getting to the 8th and 9th of February here, and things start getting pretty problematic, right? The light blue stippled areas, right, show what the projected demand was going to be given the temperature forecast, okay? And you can see that the projections here, when we go out to 15th of February was Monday, right? So this is 15th of February, 16th of February, 17th of February. This is when the projections in the demand for electricity skyrocketed in Texas, okay, because of the requirements for heating, right? And so where do things go terribly wrong? Well, things start going wrong here, right? Right at about the evening of the 14th to the early hours on the 15th of February, so early Monday, where the predictions in the light blue go up here and the actual generation drops way down here, right? So this huge gap here is the loss of power, right? The power outages. And ERCOT, the Electric Reliability Council of Texas, that manages the Texas grid, had to begin to shut down power. Otherwise, you potentially make the grid unstable, and you can then blow power plants, and you've lost power for good. So in a sense, they had no choice, right, to shut these power plants down. The bottom part of the diagram here shows this in a bit more detail, because what we're looking at here is the actual generation by source, right? So going back to the 1st of February, this top line here, the sort of light red, that is the actual generation by natural gas, okay? Green is wind. This brown over here that I'm just showing you with the arrow is coal, right? And then yellow is the sun, right? So that's solar. And the pink, solid straight pink line here at about 5,000 megawatt hours, that is nuclear. So what happened here, where the predictions of how much we needed go up here and the actual amount that is generated drops, this enormous gap between what we actually needed in terms of electricity and what occurs, that is about 46,000 megawatts of power goes offline, right? Has to go offline. Part of that is wind turbines that were not winterized. So you've probably heard of that wind turbines froze, and that is actually true. But please don't believe the news outlets that said this was all due to wind turbines freezing. That's complete nonsense, right? This was a failure across the board of frozen gas lines, power plants literally freezing up. Coal, gas, and nuclear, you all require water to run these things. And when the temperatures are, 10, 15 below, that doesn't work, right? So 185 generating plants in Texas all tripped out and succumbed to the freezing temperatures. So you can see here that 28,000 megawatts of power went offline from coal, gas, and nuclear, right? And you can see that over here. Let me just annotate this again. So here is the peak of natural gas being put out here at about 45 to 50,000 megawatts last Sunday on the 14th. And you can see that drops off precipitously here down to Tuesday and Wednesday, where we're only generating 25,000 megawatts, right? So not quite half, but almost half of all the natural gas generating capability in Texas disappears. You can see coal here goes from there to here, right? So that's a drop in coal. Even nuclear drops, although less dramatically. Clearly wind drops, right? You can see how much wind could be produced back here. In the first week in February, the amount of wind that is actually online is down here. So it was absolutely a failure across the board with an independent electric grid. Remember, 85% of all of our electricity stays within Texas as a deregulated market. So a failure of a lack of winterization of all of our facilities. Wind turbines, gas plants, nuclear, these plants work just fine up in the Northeast and in the Midwest, where temperatures routinely get to what they got to in Texas last week. So there's going to be a lot of questions asked here of the power generation people, the power generators themselves. There'll be a lot of fingers pointed, but this is not one particular generation technology. This is not wind versus nuclear or solar versus coal. It's a failure across the board. Anyway, I thought I would start with that, just to give you some context as to what has happened. So let's just get back to the discussion on fossil fuels, and then talk a little bit about nuclear. So natural gas, again, as you've just seen in that data, in Texas, natural gas supplies just about half, slightly more than half of all of our electricity. And in many other states, it is important, and perhaps even more so important in certain states. The natural gas revolution was really brought about by the gas that occurs in shale. So this is a geologic formation where the oil and the gas occurs in very, very tiny pore spaces. These, remember, are unconventional resources or reserves if you can get them out economically. The map you see here are the basins and what the natural gas community call plays. So these are the shale gas plays, and the big one you can see right under our feet, the Barnett, right? This is Barnett shale that is about 6,500 to 7,500 feet below us. So we've known that these unconventional resources are there. We've known that they've been there for quite a long time. Just we didn't have the technology to get the natural gas out to market profitably until the 1980s, when a guy called George Mitchell comes along and discovers and patents horizontal directional drilling, where you can go vertically down into the formation and turn the drill horizontally. So you only have to spend the money to go vertically once, and then you can move horizontally into the shale formation and then pump in water and chemicals and sand under very high pressures to physically fracture the rock, right? That's hydraulic fracking or fracturing. The Permian Basin out west has been a producer of oil and gas for a very long time. And the shale revolution there, again, sort of reinvigorated the Permian Basin as an incredibly important player, both here in the US and internationally, but in the US really helped drive the US to become the largest producer of crude oil in the world, and the gas, the companies that each of these little squares here is a drilling site, right? So you can just see how many of these you can get into one area. So like, you know, each of these technologies, right? And I've talked a little bit about this already. There is a large backlash against fracking. Here are some photographs from New York, where you can see placards saying ban fracking now and fracking equals death, right? And you see this kind of public backlash against fossil fuels, and you see it, as we'll talk about after the exam, you see it with the renewables as well, with wind and solar, right? So some states have banned fracking. My personal opinion, and this is just my opinion, is that I think that is short-sighted, because if it's not going to be natural gas, which is a much cleaner fossil fuel than coal, then you have to have something else, right? You have to, as I've shown you with those demand curves, you have to be able to supply electricity to the grid. This little diagram is just a summary of the principles of how fracking works, right? You drill vertically down, there's the well. You have to then case that well, wrap it in concrete to prevent any spills and leaks close to the surface. That then the well, the bore head turns horizontally, goes into the shale. Here you can see the shale down at 7,000 feet with a little blow up of what's going on around that well. And so you pump water under very high pressures with the sand and the lubricating mixture of chemicals into the rock. That then shatters the rock, it fractures the rock. The The sand is there to keep the pore spaces open, right? Because you don't want to break the rock and then have those pore spaces closed. So the sand keeps the pore spaces open, and the gas flows back to the surface. That's a very, very simple overview of fracking. So what are some of the environmental issues with fracking? Well, of course, it's a fossil fuel, and you are going to emit things. There is clearly the emission of carbon dioxide, right? So when you look at natural gas here, this little table here shows you the amount of pollution that is produced per unit of energy, and you can see natural gas is about twice as clean as coal, right? And that coal number there of 208,000 pounds of carbon dioxide is an average. So it's an average of lignite, bituminous, and anthracite. And as we've talked about, some coals are cleaner than others. So natural gas is clearly a much cleaner burning fossil fuel, and you see that on the vehicles that you see driving around town, for example. You'll see cleaner burning natural gas. Some environmentalists think that's an oxymoron. It isn't. It is true. Natural gas is twice as clean, but it's clearly not emissions free, right? Natural gas is far better than coal from a number of other pollutants. When you look at sulfur dioxides, particulates, mercury, nitrogen oxides, and so on, natural gas is a much better fossil fuel atmospherically in terms of emissions. And we're going to come back and look at air pollution a little later on. So what are the concerns then? If it's a much cleaner burning fossil fuel, which it is, what are some of the concerns? Well, certainly water is a concern, right? It takes a lot of water to frack a well, depending on how deep the well is and where you are, anywhere between 2 to 5 million gallons of water to frack one well. And there are thousands and thousands of wells. So yes, you are using a precious resource here, water, to frack the wells and get the natural gas and the oil out. And this infographic here just tries to illustrate that again, depending on where you are and depending on what your consumption patterns are, you can, one frack job can produce enough water to supply, somewhere between 10 to 65 families with drinking water for a year. But I think that, like everything environmentally, this has to be kept within some sort of context, right? Yes, fracking uses water, but when you look at just Colorado, let's go outside of Texas for a minute and look at Colorado's water usage, right? Fracking in Colorado uses less than 0.1% of all the water use in that state, right? Agriculture is by far the dominant water use. And I'll make this point much later on when we get towards the end of the course, everyone, and we talk about water resource issues, right? Agriculture consumes vast amounts of water. So I'm not trying to suggest that water use in fracking is not significant. It just has to be set in context. The other thing that I think is important to understand is how things are skewed in the media, right? This is a very common diagram. You'll see this in the media a lot, where those who are anti-fracking will draw a picture of a well, and then they'll draw an underground aquifer, which is a geologic unit that contains water. So there's our drinking water. And then there are all the hydro-frack zones with all of this red pollution migrating upwards towards the aquifers. Well, I caution you when you see images like this, right? Because the reality is that our underground aquifers are generally much closer to the surface and generally very far away from the formations that contain the oil and gas. For example, the Barnett Shale is 7,500 feet underneath us here in the Fort Worth Basin, right? Our aquifers are much closer to the surface. And unless there is leaking of chemicals and fluids at the surface, which in fact there are sometimes, no doubt about that, right? When they don't case the wells properly, then yes, pollutants can leak into our water. But there really has been very limited pollution of groundwater as a result of fracking. Those chemicals stay deep underground for long periods of time, right? Well beyond human timeframes here. So again, I caution you just to, when you're reading up or when you're listening to the media about the pollution of groundwater from hydraulic fracking. There have been instances, and it is a concern, especially where aquifers are close to the fracking zones, but that is the exception rather than the rule, right? The rule is that the fracking occurs much deeper underground. One thing that is a concern, another thing that is certainly a concern, right, is methane. When you burn natural gas, that's CH4, right? And methane is a very, very potent greenhouse gas. Now, we're going to come and look at greenhouse gases in quite a lot of detail with climate change. But you know, you've heard of carbon dioxide being a greenhouse gas, water vapor is a greenhouse gas. These are the gases that absorb energy given off by the Earth and keep our planetary temperatures warm. But methane is a much more powerful greenhouse gas, right? If you put the same amount of methane and carbon dioxide into a closed environment, methane has a much more powerful, what they call global warming potential. It's about 80 times stronger than carbon dioxide. And the reality is that methane does leak along the transportation network, right? And those in the climate community are concerned that all of the work that we're doing on trying to reduce carbon dioxide emissions may actually not really amount to very much if we don't take care of the methane. So that's a little bit on natural gas. There are obviously pros and cons, as there are to every single one of these generation technologies. So, you know, check yes or no. Natural gas is here to stay, right? Again, for quite some time. And if we're going to tackle the climate crisis in a serious way, then I think the first thing we have to do is absolutely get rid of coal, and natural gas is doing that, right? We're seeing the rapid displacement of coal-fired power plants by natural gas power plants. So here's another one. Let's talk about nuclear then, and we'll wrap this up. When we come back from the first exam, we're going to examine renewables, right? Renewable energy. And so when we talk about renewable, you probably think of solar and wind, or hydropower, or biofuels. Whether a generation technology is renewable or sustainable, those two are two different terms, right? Technically, a renewable source is one that replenishes itself naturally. The question is that sustainable? Is it economically sustainable? Is it politically sustainable? And these are two, I think, interesting terms to just kind of keep in the back of our minds as we look at nuclear energy, right? Because technically it's not renewable if we're using uranium, for example, as the fuel source. But is it sustainable? Well, that's something we'll examine. So on the left here are two cooling towers from a nuclear power plant, and you can see the big smiley faces. Those in the nuclear industry suggest that this is absolutely the way forward. On the right is an aerial photograph of the Fukushima power plant that was badly damaged in 2011, and I'll touch upon that a little later on. Okay, so nuclear energy, the generation of power from nuclear is, again, like I suppose all of these technologies, controversial, because I think one frequently thinks of this, right, when we think of nuclear power. And so that is something, I'll show you the nuclear fuel cycle in just a little bit. And I want to make sure that you understand there's actually a very large jump from generating power from the nuclear reaction to generating weapons from the nuclear reaction. Just as a source of context here, these are the top 50 nuclear generating countries. You can see the United States produces the most power from nuclear, so 800 plus billion kilowatt hours. Don't worry about that actual number. It's just a lot of energy that comes from nuclear. And then you can see these other countries moving off to the right here. So the United States, France, China, Russia, South Korea, those are the 5 biggest producers. But these countries that I've scaled up here show the countries that generate the top 5 as a percentage of their energy profile, right? So the US generates about 20% of its electricity from nuclear. You can see France is just over 70%. 72% of all the power in France comes from nuclear, right? And there's countries there that you may not think would be on there, right? Sweden gets 40% of its power from nuclear. So again, nuclear isn't going to go away anytime soon, but there's a really interesting mix here of some countries that are embracing nuclear, like the United Kingdom, that want to build more nuclear power plants, and the US is also keen on building nuclear power plants, as is India, wants to build more of them. There are other countries like Germany who want to get rid of them completely, and Japan. So there's quite an interesting dichotomy beginning to emerge in terms of nuclear. So the US, of course, led the world into the nuclear age. And President Eisenhower in 1953 suggested that we would lead the world out of the nuclear age. This is a very famous speech he gave to the UN, the Atoms for Peace speech. They even had a stamp made where President Eisenhower suggested that nuclear-powered generators would provide power that would be too cheap to meter. We wouldn't even have to worry about paying electric bills given the nuclear reaction. Of course, that has proven not to be the case. A quick look at the US. This is the latest data that I can get my hands on. We currently have 97 power plants that are licensed to operate. The numbers here show how many nuclear units are there. So we have 97 nuclear reactors in the US. You can see 2 in north central Texas here. Those are the 2 down near Glen Rose, and we've got 2 down near the coast, right? So there are 4 nuclear power reactors in Texas, but quite an interesting slant here, right? When you look at nuclear power, much of this is east of the Mississippi, the industrial Northeast. Now there's a couple in California, 3 in Arizona, and 1 in Washington, but nuclear is essentially a Midwest and East Coast phenomenon. This is the nuclear fuel cycle. I want to just give you a quick overview of this. With one caveat, there are different types of nuclear power plant, and there's a whole range of new technology power plants coming online, which beyond the scope of this course, I just want to give you an overview of the most commonly used type, the one that is most used out there, and then we can talk about the environmental implications of that. So this is the nuclear fuel cycle, sort of my attempt to simplify the nuclear fuel cycle. And there's 2 important components here, right? There's what we call the front end of the nuclear fuel cycle, which is up at the top here. And then down at the bottom is the back end of the nuclear fuel cycle. So the front end of the nuclear fuel cycle is everything that involves getting the fuel, which in this case it's uranium, mining that, milling it, getting it out of the rock, converting it and enriching it, right? Increasing the concentration of it to the point where you can produce fuel, right? So the isotope is U-235 that is used, uranium-235. Okay, that is what is used in most conventional nuclear power plants. So you mine it and you convert it and you get it to this point where it's enriched. This is the point where you have to make a gigantic step from enriching it. And when I say enriching it, we're enriching it to a value of about 3%, okay, of the total volume, as opposed to moving up here to weapons grade uranium, which is 20 to 25%. And that is much more expensive, technologically advanced. So I just wanted to make that point when we think about enrichment and the controversy surrounding a place like Iran, right? This is the part of the arrow that people are concerned about in terms of global safety. So what happens is you get to a point where you're enriching the uranium, and then you do this, right? The uranium is processed into these tiny little pellets like you see on the top left-hand side here. And so here's a pencil in my hand. And that little eraser head on the top of the pencil there that looks like a uranium pellet is about, the size of what a uranium pellet actually is. Those little pellets are then dropped down into a fuel rod, which is about 12 foot long, right? A thin aluminium rod. And then they take about 100 of those rods and they bundle them into a fuel assembly. And you see that on this photograph here. So this column right over here, that is a fuel assembly of about 100 fuel rods. And in a typical nuclear reactor, there's something like 250 of these fuel assemblies, right? So that's the fuel for a nuclear power plant. Uranium that is processed into these pellets and then put into these fuel rods. Okay. The reaction itself is extraordinarily powerful and elegant, right? You cannot, and I think I made this comment at the outset, you cannot get a bigger bang for your buck than nuclear energy. It doesn't happen because of the power of splitting the atom, right? So you've got a U-235, and this is essentially how it works. You take a uranium-235 atom and you bombard it here with this little chap, and he is one neutron, right? So here is a uranium-235, and you bombard it with a neutron. That then becomes U-236, and it becomes unstable, and that atom splits apart. And as it splits apart, it releases a huge amount of heat, and it also releases further neutrons here that can then go out and seek out another U-235, causing that to split, right? And releasing heat energy and more neutrons in what we call a chain reaction. Okay? It's not a nuclear explosion. It is a catalytic chain reaction that continuously releases huge amounts of heat. And the elegance of the nuclear fuel cycle is that you're just taking that heat that is produced to heat water to create steam. Okay? So it's just another way of creating steam, but it is the most efficient and it is the most powerful way to create steam. So again, this is a generalization of what a typical nuclear power plant looks like. This is called a pressurized water reactor plant. This is the key part of it. This is the reactor, okay? And down on the right here is a photograph of a reactor sent to me by a friend of mine who worked at a nuclear power plant in Georgia. And right down at the bottom here, you can see this is where the fuel assemblies would be, right? Right down at the bottom there, they're in water. And the red box here in the reactor core is the fuel assembly. So that's where the uranium-235 is. That is where you bombard the U-235 with neutrons. You set off the chain reaction. You create vast amounts of heat that is then used to heat water. It actually heats the water to a temperature that is too hot to create steam. So you run that superheated water through what is known as a steam generator here, right? That heats water to actually create steam. That steam then turns the turbine, turns the generator, produces electricity. That water is sent through a cooling tower and sent back through the system. So the clouds that you see coming off these towers, there's no emissions there, right? That is just simply condensed water vapor returning back as clouds. So that's the fundamentals behind the generation of electricity from a nuclear power plant. Simple, elegant, you can't beat it in terms of the output, right? That's all the front end of the nuclear fuel cycle, right? Now we move to the back end of the nuclear fuel cycle, and this is where things get a little trickier, at least environmentally, right? So here's your nuclear reactor, and you're generating electricity here. Now the problem is, what do you do with the waste? Because eventually those fuel rods become radioactive, right? And they're no longer usable, and you have to store them. And the difficult part is you have to store them for 10,000 years before they become safe, right? And that is, in a nutshell, the controversial issue when it comes to, or the most controversial issue, I suppose, when it comes to nuclear power, right? How do you store that? You put it into interim storage. In many nuclear fuel plants, some of that spent fuel goes through reprocessing, okay? We don't have any reprocessing here in the United States. No plants reprocess their spent fuel. Part of that is perception, part of it's the economics. It's very expensive. It's perceived as actually quite dangerous because it produces material that could be used in nuclear power, and it's not cost effective. So we don't have any spent fuel reprocessing here in the US. They do in France. But ultimately, the back end of the cycle has to focus on final storage, right? Final disposition. And therein lies the problem. There are no permanent storage facilities anywhere in the US or anywhere in the world. So in summary, for waste, okay, almost all of the radioactivity associated with nuclear waste is focused on what we call HLW, which is high level waste, right? the spent fuel. That's the most significant. As I said, has to be put away for 10,000 years. And at the moment, all of that occurs on site in temporary storage. So here that they're all stored in these containers, these sort of casks over here. The fuel rods, as you can see, are right in the center. Okay, and these are really expensive, very sophisticated containers. They're bomb-proof, right? Concrete barrels. They've got they're lined with boron. And boron, I should have pointed this out in the nuclear fuel cycle. My apologies, I forgot. Boron absorbs the neutrons. So that's how they control the nuclear reaction, right? There were control rods that you put back into the reactor core, and those control rods absorb the neutrons and shut down the reactions. But here's one of these containers going into a temporary storage facility in a nuclear power plant in Vermont, which has now actually been shut down, but the storage facility is clearly still maintained. And here is one of the containers being transported. So, people are concerned about nuclear waste being transported around, but at the moment we haven't had any issues or accidents in the United States. This was supposed to be the first permanent storage facility. This is a facility called Yucca Mountain in the Nevada desert, a rather nondescript ridge where they spent, well, it's certainly more than 20 billion, but from what we know, at least $20 billion doing all of the preparation, the geologic studies, trying to get this ready for permanent storage. The idea here was that you would build a series of underground sort of repositories or catacombs, if you like, and this was a region where the water table was far away from any waste, so there would be essentially no chance of contamination. And you would bring the spent waste here into Yucca Mountain and put it into these storage facilities and lock it away forever. The first nuclear waste was supposed to go into Yucca Mountain in 1998. President Obama shut that down in 2010. No waste ever made it to Yucca Mountain. It became too expensive, too controversial, and too embroiled in lawsuits. And one of the concerns was getting the nuclear waste to Yucca Mountain. So here's Yucca Mountain over here in Nevada, just northwest of Las Vegas. And the colors that you see here are the counties, and the darker the color, the higher the population, the counties through which the nuclear waste would need to be transported to get to Yucca Mountain. So from the South Texas plant, it would either have to go up there or through there, and then make its way through Yucca Mountain or through these populated areas. And there was an enormous backlash against transporting this nuclear waste, even though they would be transported on rail cars in these bomb-proof caskets. It proved to be too controversial and too problematic. So in 2010, Yucca Mountain was sealed up, and all the nuclear waste is currently stored on site. One of the other things, let me just comment about nuclear, this is often overlooked, I think, is the economics, right? Any new technology for generating power, or I suppose anything, but certainly when it comes to power, any new technology is going to thrive if it is economically and politically viable, right? If it doesn't make sense economically to do it, it's not going to happen. And this is one of the problems with nuclear. It's just simply the economics, the costs. So it costs somewhere between $7 to $12 billion to build one nuclear power plant, vastly more expensive than any other technology. And then that nuclear power plant has to be decommissioned once it's gone through its life cycle. So all plants in the US are licensed to operate for 40 years. They can apply for an extension, and almost everyone has and been granted. There are one or two exceptions. But the bottom line is that the power plants that were built in the 1960s and the 1970s, right, will all be offline permanently by about 2040 to 2050, because that is when their 80-year cycle will be done. Then they have to be dismantled. So unless you're going to replace nuclear with nuclear, these power plants will all come offline. And it costs huge amounts of money to decommission them. So when you pay a utility bill, if you are a utility payer, there's a very small amount, I think it's like $0.015 of every utility bill every month goes into this mutual fund, which is the decommissioning fund. And there's real concern that like Social Security, that will not have enough money by 2050 to be able to pay for the decommissioning. So this is the Texas situation. Just quickly, there are 4 reactor units. There's the South Texas project in Bay City. That's the photograph you're looking at here. Those are the reactors in the center. And then there's Comanche Peak. Nuclear energy could supply, I should have put could in there, about 8% of the electricity generated in Texas. In 2020, if you remember back to the very first bullet points, it was about 5%. But this is the big one, right? This is, I suppose, the major concern, environmental/social concern, and that is what happens when there's an accident, okay? And the title of this slide is NIMBY. That is an acronym that stands for Not in My Backyard. And this is really a kind of environmental backlash, if you like, or environmental acronym that really started with the nuclear industry, right? Where you go, okay, maybe we should have nuclear power because it is just so good in terms of the amount of energy that it produces, but not in my backyard. You can build it somewhere else. We've had 3 major nuclear incidents. One occurred on 3 Mile Island in Pennsylvania in 1979. It was essentially averted. It was a partial meltdown where the reactor began to fail, but they were able to save it. So there was no radiation leak and there were no deaths from 3 Mile Island, but that got people's attention. This was the big one in 1986 in Chernobyl in the Ukraine. An old technology pressurized water reactor that went wrong. They were running some tests. The tests went wrong. They couldn't get the control rods back into the reactor core. Their safety protocols failed. There were too few people at the plant, and the reactor melted and blew apart. This was enormously problematic, right? 1986, there were no iPhones, there was no YouTube. Information came out very slowly about this accident, but eventually the USSR, the Soviet premier had to say, we've had this accident, and they evacuated the nearby town. And this animation will show you, as it begins to run, it'll show you the emission of the radioactivity from that reactor. So this is radioactive material. The darker the color, the more of it. So the initial plume went north into Scandinavia. Then the wind shifted down, coming out of the north to the south, and that moved the plume down south towards the Black Sea. And it's not that the whole of Europe became contaminated, but the fallout certainly contaminated soils and people in and around the power plant. And the toll is still being tallied up. We don't know how many people have died as a result of radiation. Some put the estimates in tens of thousands, but it was a major nuclear accident that was enormously problematic for the nuclear industry. I'm going to skip that one. Then there was also the Fukushima one in 2011. So that's a quick summary then of what has happened in the last week. A little bit about natural gas and a little bit about nuclear. I didn't want to skip these. I thought it would really sell you folks short if we didn't cover natural gas and nuclear. But as I say, this will not be on the exam for next week. So watch this in your own time, and then we'll meet on Tuesday for an exam review.